Okay, so when we're talking about forces, we need to know, we need to be able to draw a free body diagram of this object. So the free body diagram rules say, number one, a dot represents the object, and number two, all forces start on the dot and point outwards. So our first example here says, imagine a book sitting at rest on a table. What forces act on it? If I need to first choose one object to look at. So the question mentions a book and a table. I'm just going to look at the book. And what it says is we draw a dot to represent the object. So there's the book. You don't have to be a great artist. It is nice if you can get a solid dot though. What forces act on this book? Well, force of gravity is pulling this thing straight down. That's why it's not floating around. But we could ask, why isn't the book falling down? Why is it not hitting the ground? And the answer is obvious, because the table's there, right? The table's supporting it. That support is another force. So this one's less obvious, but the force that the table supports the book with to prevent it from falling down, we call that the normal force. Anytime you've got one object supporting another one, we call that the normal force. I know that the book is not accelerating down towards the ground, it's not falling to the ground. If that's true, it's kind of like a tug-of-war. This force must be pulling with the same force as that force. The two forces are equal. The forces are equal, and we know that they're equal, again, like a tug-of-war. If both teams pull with the same force, then the rope doesn't move. Same idea here. These two forces pull with the same force, the book doesn't move. In example number 2, it says, now we've got this... now I'm pushing this book. The book is now sliding to the right. So same idea. We could say, well, here's a dot to represent our book. We still have force of gravity. That's acting straight down. We've got a normal force. That's going straight up. The book is still not falling to the ground. Those two forces cancel each other out. But I'm also pushing this book to the right. So you could say, well, there's a force coming across here. We'll call that applied force. I'm pushing it to the right. And if the book is sliding along the desk, then there's got to be some friction. We've talked a little bit about friction. Here's friction. Friction is resisting that applied force. I'm not sure now if the book is speeding up or slowing down or what's going on here. I know that it's sliding to the right, but I'm not sure. I can't say for sure that those two forces are equal or not. So in example 3 it says we've got a 10 Newton water bottle being pushed to the right by an applied force of 40 newtons. There is a force of friction of 30 newtons that's resisting the motion. Find the net force acting on the bottle. Alright, step 1 with these kind of questions, always let's draw ourselves a free body diagram. Just like we've talked about before, gravity pulling the water bottle down. We've also got this normal force, right? It doesn't mention a table in this question, but I'm going to assume that this water bottle is being pushed along on some surface. It could be the table or the floor or whatever, but something is supporting this water bottle. It's not freely falling down. And like we've talked about before, those two forces are equal. That'll be common in grade 11 physics, that those two forces are equal. They're not always equal, though. There are exceptions to this. This question also mentions that there's an applied force. We've got an applied force coming out this way. That says FA. Ooh, let's see if I can make that a little nicer. There's FA. There we go. And we're given a number here. This is a 40 Newton force. We also know that there's a force of friction. Force of friction is here, resisting back this way. And that is 30 newtons. We were given another number in here. It also mentions that it's a 10 Newton water bottle. So we should go ahead and put that on. If it's a 10 Newton water bottle, they're talking about weight. Weight is force of gravity. So if it says it's a 10 Newton water bottle, force of gravity on this thing, 10 newtons. We already talked about how the normal force is equal to the force of gravity. Normal force, also 10 newtons. Those are a couple things we don't really need in this question, but we'll put them on there since they were given. The question then says, go ahead and find the net force acting on the bottle. Well, the net force, we write it like this. We write a sum of forces. The sum of forces is just equal to F1 plus F2 plus F3, however many forces I've got, plus dot dot dot. However many forces, we're just going to add them all up. But net force also implies unbalanced forces. And remember we said the normal force and force of gravity are equal? I don't need to include those forces in here. So when I'm looking for the net force, I'm just going to add up, and it's going to be applied force plus force of friction. Those are my two unbalanced forces. Before I can stick any numbers in here though, just note that the applied force is to the right in my drawing, and friction is to the left. They're in opposite directions, and do keep in mind forces are vectors. I didn't stick any vector signs over here, but these forces are all vectors. If they're vectors, we've got to treat them as vectors, which means we need to include positive and negative directions in there. So I'm going to go ahead and choose a positive direction. Let's make another little color in here just so you can see it. I'm going to say this forwards direction. We could say up as well if you want. Up is positive, forwards is positive. That's an arrow there. If those two directions are my positive directions, then when I sub numbers in here, we got to include those signs. So the sum of forces is applied force. Applied force is to the right, that's my positive direction. Applied force goes in as a positive number. Friction is to the left, that's a negative, so I'm going to put that in as negative 30. Sum of forces then, 40 minus 30, 10 newtons. And whenever I get an answer, we've done this lots with other vectors, just like displacement and stuff like that. Whenever I get an answer here, it's in my positive direction. That's going to be to the right. So the net force then, or the sum of forces you could say, is 10 newtons to the right. And I know you guys like me to box my answer in a nice bright color, so there we go. Nice bright red color for you. There's the net force acting on the bottle. Alright, so we've got Mr. Graywell and Mr. Jack fighting over the last can of Coke. Shame on those guys, they shouldn't be drinking Coke. Anyways, we won't judge them for that. Mr. Graywell is pulling with a force of 120 newtons north. Let's go ahead and start off with a free body diagram. Let's say here's a dot, here's his force, I'll call it F1, 120 newtons. And Mr. Jack is pulling with 80 newtons east 20 degrees north. So I'm just going to stick a little dotted line here. We'll change the color. There's straight east, and his force is going something like that. His force, I'll call it force 2, that's 80 newtons. And right in here we've got 20 degrees, so there's east 20 degrees north. We're going to have to break these vectors up into components. So force 1, Mr. Graywell's force, is already straight north. That's already on the y-axis. I don't need to break that up into components. There's no x component. But for Mr. Jack, he's going to have an x component and a y component. That's a y component there. So we're going to need to find those. F2x is going to be, it's whatever the magnitude is times the cosine of 20 degrees. And it's cosine because that's the adjacent. Remember, cosine's adjacent over hypotenuse. F2x is the adjacent side, so we're going to use cosine here. And F2x works out to 75.175 newtons. So I'll stick a box around there. This isn't any kind of a final answer, it's just the one component of that force. We need to do the same thing in the y direction. It's 80 sine 20 degrees, and again that's sine because the y component is opposite the angle. So it's going to be a magnitude of the force times the sine of 20 degrees. And that works out to 27.36 newtons. That says newtons there, newtons. We're going to need to take those two things and add them with the first vector. So the first vector, let's change a little color here. How about a nice blue? The first thing we're going to do is we're going to add the two x components. So remember, sum of forces in the x direction, that's equal to f1x plus f2x. When we add these things, f1 does not have any x component. So when I say sum of forces in the x direction, f1x is just 0. You don't really need to show this step, but I'll show it just so you can see it. f2x is 75.175 newtons. Sum of forces in the x direction is just 75.175 newtons. Put a little box around there. I should say the direction here, actually. Let's see if I can squeeze that in somewhere. Let's get rid of that little bit. We'll go back and we'll say f2x, you can see, is pointing to the east. So this thing is in the east direction. There we go. And I should have said, I always seem to do this, but I should say I'll take north as positive and I'll take east as positive. Okay, there's my positive directions. We should add that stuff in. I want to add stuff in the y direction as well. So let's kind of stick a little line right here, and we'll look for sum of the forces in the y direction. That's just going to be f1y plus f2y. And that's a y there. Sum of forces in the y direction then. Here we do have multiple forces in the y direction. So I'm going to have to add f1 in the y direction. And remember, since f1 is pointing straight north, then the entire 120 newtons is pointing north. The whole thing is in the y direction. That's not true with f2y, or with f2, I mean with f2 we had to break it up into components. We found that y component to be 27.36 newtons. So the sum of the forces in the y direction, if we add those two things together, we get 147 newtons. 147.36, I guess, newtons. And that's in the positive direction, which we said is north. So both those vectors are pointing north. So this force here is going north. I'm going to go ahead and redraw my triangle then. So let's switch this. Try another color. How about red? If I was to redraw my triangle, I know how far it's going in the x and the y direction. So here's the y direction. Here's the x direction. The y direction, this is 147.36 newtons. That's a 7 right there. And in the x direction, it's 75.175 newtons. This is actually what I'm looking for right here. Right? This is the net force. And of course, we're going to need to have an angle over here as well. So I'm going to come up to the top. Come up over here. And we're going to go ahead and find what the net force is and that angle is, and then put it all together. To find the net force, we've done this a number of times now with different kinds of vectors. Just like in displacement, if I know my x and y components, I'm just going to use Pythagoras. So it's this thing squared equals 147.36 squared and 75.175 squared. When I go ahead and use Pythagoras, I find that this is 165.42 newtons. Remember, that's not an answer, not quite the final answer anyways. There's part of my answer. I also need an angle. I know that tan theta is going to be opposite over adjacent. So looking at that red triangle, opposite the angle, 75.175. Adjacent, 147.36. We'll divide that, hit inverse tan or shift tan. Make sure you're in degree mode. We get about 27 degrees. Again, none of those are final answers. To write my final answer then, I need to say sum of forces in total is, and we're going to have to round that 165 for significant digits. It looks like we got 2 sig digs, so this is approximately 170 newtons. It's 165, but when we round up, 170 newtons. And then we've got to write our direction over here. This 27 degrees is touching north, or if you look at my triangle, if I just write over it again, the vector here is going north first, and then we're going east second. So I'm going to say north, then 27 degrees. than east. And that there is my final answer. And I'll double box that answer. There's the net force. Remember, this is only the net horizontal force, but that's the net force that acts on this pop can. That's it.